So the last talk today will be by Kamnitzer, and the title is Categorical Lie algebra actions and braid group actions.
Well, thanks very much for the invitation. So this talk is somehow parallel, but a little bit orthogonal to the last talk. So it's also based on joint work with Sab and Khovanov, and much of it is also with Tony Loreto. So I'm going to be focusing on. So earlier, let's go back to the beginning of the conference. We heard Misha and then Aaron tell us about this two categories which categorify quantum groups. And so one purpose of this talk is to discuss actions of those two categories in algebraic geometry on derived categories of coherent sheaves. And another purpose of this talk is to explain how one can use actions of those two categories to produce actions of braid groups, either in that geometric context or in other contexts. And so from the point of view of knots, this actions of braid groups can lead to, or do lead to knot invariance. Well, I'll get there in a few words. So we're going to be working in this algebra geometry context, so let's focus on that for the moment, just to introduce that. So take X to be a smooth variety of the complex number. And in this talk, we're going to be interested a lot in the following category called D of X, which is the derived category of coherent sheaves. So it's derived category of coherent sheaves, right? And if you want to think about this category in a sort of a slightly easier fashion, it's the same as the category of complexes of algebraic vector bundles on X. So we're going to think of it as kind of like some kind of invariant of X. So instead of studying the cohomology of X, we're going to study this category associated with X. And we're going to try to do some operations on these categories. In particular, we're going to be interested in equivalences of this category. So we're interested in what I'll call auto-equivalences. X, which means the collection of all functors C from the E of X to itself, which are equivalences categories. And usually we'll only be interested in them up to the isomorphism of functors. Isomorphism of functors. And in particular, we're mostly going to be interested in those kind of interesting autoequivalences. So there's some boring autoequivalences which come from automorphisms of X, but then typically there'll be also some very interesting autoequivalences not coming from automorphisms of X. So, and one goal of this talk will be to construct braid group actions on X. So we'll be interested. Braid group on n strands to this auto-equivalences section. So let me mention some motivation for doing so. So the first piece of motivation is that these kinds of actions of braid groups can lead to construction of knot invariance, homological knot invariance. So, for example, the original Khovanov homology can be reconstructed, if you like, in this form. And as Sabin explained, more generally, one can try to use some of these ideas to categorify certain Rashtikin tribe invariants. And for example, you could categorify the Rashtikin tribe invariants associated to wedge powers in the standard representation of SLN. So there's some homological non-invariants which can be can be defined using these kinds of braid group actions. The second motivation comes from homological mirror symmetry. In particular, in this context, I can mention a recent work by Braverman, Malik, and Punkov, where they proposed construction. So they proposed, they conjectured that one should be able to construct equivalences, which are lifting the monodromy in quantum homology. I don't really want to go in this direction too much, but the kind of main result that I'll get to at the end provides an important step in checking their conjecture for this quiver varieties, which is a class of varieties that they made this conjecture for. Okay, so as I say, from some way I'm motivating this talk is that we're interested in constructing braid group actions on these derived categorical coherent sheaves, and say for these reasons, and in order to construct these braid group actions, we're going to use the two categories that we heard about at the beginning of this conference from Misha and Aaron. So let me explain why those are relevant. So we will get group actions. We will start with quantum group actions, or rather categorified quantum group actions. So let me explain why this is a reasonable thing to do. So consider the following map. The braid group on n expands to the group SLN, which takes the generator of the braid group sigma I. So my braid group will be usually thought of with generator relations. So sigma I is the guy at the cross spot. So sigma I will go to the matrix in SLN, which has say 1 here, -1 just below the diagonal, and 0 everywhere else. This is in the ith spot here. And this is a group homomorphism. So, and more generally, there's a group homomorphism constructed by Lustig from the braid group to the quantum group, or to some completion of the quantum group. So if V is a, say, finite dimensional representation of SLN, or this UQSLN, then the braid group Bn acts on B. So the main goal of my talk is to kind of describe this categorical version of this statement. But before I get to that, let me slightly generalize this statement. So suppose that gamma is any graph. Then we can construct a braid group E gamma. The associated braid group is generators sigma I, where I means capital I, which is a set of vertices of my graph, and relations sigma I. The generators commuters are not connected to that. I not connected to J, and the generator is braided with the corresponding vertices in the graph are connected. Okay, so then the Bn is equal to B gamma, where gamma is the graph An minus 1. An minus 1 is the graph, the linear graph, N minus 1 vertices. also associates the graph, we have G gamma, which is a Categorical Lie algebra. Simply lays Categorical Lie algebra with generators EIs, FIs, HIs, some usual Categorical relations. Oh, that's all. And so the generalization of this map here is there's a map from the braid group associated with gamma to certain completion of the quantized universe resolving algebra of the Categorical algebra associated with gamma. So which generalizes this. So this is a quick run through. I think this is due to loosely. So in some sense, there's kind of two appearances of braid group in representation theory. One is this what you might call kind of internal braid group, this one described here. And the second braid group is kind of the one that you maybe usually think about, which is when you have a tensor product of representations of a quantum group, the braid group is acting by permuting the tensor factors. And the two are sometimes related in this how dual situation, but in general they're unrelated. And so in my talk we're going to be concentrating on this kind of internal braid group. So, anyway, as I mentioned, the idea is to come up with a categorical version of this map. So this idea was, I guess, suggested and partially carried out by Rouquier and Rouquier. So, study categorical of this map. This map from the braid group to the quantum group, or you could say a map from the braid group to this map. So now I should explain to you a little bit. So we need to have a categorical version of this side, and that was described earlier. But I'm going to sort of, and also in Simon's talk, so it's going to be a slight over repetition, but I think maybe it's good. Anyway, so if V is an integrable representation of this quantum group, G gamma, then, so just the representation of vector spaces, then we have a weight decomposition of the representation. So this is X, here's the weight lattice. So this controls the action of the HIs. We have our operators EI, which move you around between the weight spaces. So these alpha I are the simple roots. FIs move you in the opposite direction. And we have the conjugation relation, EI FI minus FI EI, acting on some weight space V of mu is the identity matrix times pairing mu with alpha. And the second maybe thing which I'd like to emphasize that we have is we have this Serre relation, which is that these operators obey the following rule, where, as usual, this EI upper 2 means EI squared divided by 2. So the way I think about this categorifications that Misha and Aaron talked about earlier in this conference, or actually the way Misha first explained to me about them, was that you think about this kind of linear algebra data, and everywhere you see vector spaces, you put categories, and everywhere you see linear maps, you put functors. If one does that, we arrive at the following notion. So, a naive categorical G gamma representation is the following data. One collection of categories D mu for mu and x. And keep in mind, for me, these categories will eventually be the coherent sheaves in certain varieties. functors, EIs, which will move me around just like the linear maps moved me around before. And, well, that's all the data, such that, notice I called it naive, such that we have these kinds of equations like what's happened over this time, EI FI is isomorphic to FI EI, plus a bunch of copies of the identity functor acting on the continuum. Okay, and that's if this number is positive and this number is negative, you write a similar relation. And also the analog of that Serre relation is isomorphic to EI to EJ plus EJ EI. Okay, so at this point we comment, well, this looks not so bad, but it is sort of a bad notion because at this point I just wrote that this should be isomorphic to this without specifying what the isomorphisms are. So a much better notion is to build the data of the isomorphisms into the action. And that's what these two categories that we heard about earlier in the conference are doing. So a true categorical representation of gamma is a two-functor from this two categories. I have no idea if I'm using the right notation. Anyway, U dot G gamma to the two category of all categories. So this is the two category defined by Khovanov-Lauda. Or possibly one might use the very similar two category defined by Rouquier. So a true categorical representation of G gamma is such a two-functor, and just to spell out what that means, we have similar data. So we have categories, we have functors as before, exactly the same data there as before, but at the kind of third level, we have now the third level of data, which is natural transformations of functors. Which somehow have pretty pictures associated to them. So like this one, or this one. And this was, I'm going to make each one a separate line. So if you remember from the previous talk, this was supposed to be a map from natural this will end up being a natural transformation like this, and this will end up being a natural transformation like this. And then some other natural transformations. But let me just emphasize that the way I think about it is the purpose of these natural transformations is to pin down the isomorphisms that I wrote as just some abstract isomorphisms here. And then the kind of relations, here we have kind of relations in little functors. Here we have some relations on the level of natural transformations. Those relations were what took many pages in Aaron's time. But it's a beautiful theory. Okay, so as I mentioned before, the one thing I wanted to tell you is that that we want to have a categorical version of this map from the braid group to this UQG gamma. So one could really take this statement very seriously and invent some kind of two categorical version of the braid group and define some two-functor, but Savin and I are not so categorically minded enough, so we didn't do that at all. But we have the following theorem. So this theorem is Savin, and I guess building on earlier work I'm showing in Rouquier, and I guess part of it also with Stony, I guess. Anyway, so if this collection of categories carries true categorical G gamma I. So exactly this thing, plus some additional technical assumptions such that each E mu is a graded triangulated category, and some restrictions on the Hom spaces, that minus L from the identity in itself is 0 for L positive, and Hom 0 from the identity to itself. Okay, so some technical assumptions which will be valid in the situation we'll apply it later. Then for each I, there is an equivalence of categories sigma I from the derived category, from this category D of mu to this category D of SI mu. So this SI mu denotes action of a Weyl group on the weight lines. And these satisfy the braid relation. So in particular, you do get exactly a map from the braid group, say, to the autoequivalences, the group of autoequivalences of D0. So the kind of basic idea of this, or what the definition of sigma I is due to Schwang and Rouquier, and sigma I acts by the following complex. The complex goes here. K F equals 1. Where K is equal to the pairing mu with alpha I. Maybe minus pairing mu with alpha I. And I assume that thing should be positive. Okay. So this is kind of makes sense because you want to go from this weight space to this weight space. And each one of these functors individually take you from that weight space to that weight space. And it turns out you can fit them all into a nice complex, and that complex will actually be an equivalence between this category and this category. This is a complex of functors. At some point you have to change from having a complex of functors to having actually a single functor. And that's where you use some of these technical assumptions. So it's just all the possible things which get you to the right weight space. So you kind of go backwards 2 steps and then go forwards those 2 steps. Yeah, I'm adding one each time. This categorifies some formula proved by Lustig for this. Remember, this theorem is supposed to be the categorification of that group homomorphism that I mentioned from the braid group to the completion of this quantum group. And so sigma I is taken to this kind of, the obvious thing here, the alternating sum of this thing. So this is a formula proved by Lustig. No. Remember, this is the internal braid group, not the braid group related to the R matrix. On the other hand, there is this theorem proved by delano loreto in a certain case, and proved by us in a different case, which is that when you're in this Howell-Dual GLM situation, the 2 braid groups actually line up. So there is one case where the braid group overlap, but generally you should think that there's 2 different braid groups, so one acting by permuting tensor factors, one related to the R matrix, and the other internal braid group. But sometimes they do line up, and that's exactly the Rashid and trivariance we can categorize.
Sorry, I have a quick question.
Yeah.
So these I's over here in your hypotheses, are they just the identity functors?
Correct. This is the identity, yeah. These are the only executes. These are the identity functors. Okay.
K. Sorry,
K is this. minus the pairing of mu with alpha I. And if this pairing is actually positive, then you have the same complex but with either place values.
Does it say the K?
No. This K here is a field. So the identity functor should have one-dimensional space of endomorphisms in degree 0 and in negative degree no endomorphism. Okay, so anyways, all this was kind of slightly abstract. Now I want to get back to the geometry. So I want to show you, first of all, an action. Actually, it's related to Savin's talk. An action. One of these categorical actions. Define some varieties. So let me write that again. So we will now. So we fix two numbers, little n and capital N, and we study the variety of all little n step flags in Cn. So sequences of subspaces on Cn with n things in the sequence. So this disconnect with space, because I haven't specified what the dimensions of these VIs are. So it breaks up into connected components according to the dimensions of these VIs. This mu will denote what the dimensions. So the VIs are more precisely will denote the jumps between the dimensions VI, these VIs, and mu is some partition of capital N with n parts. Okay. And now we'll let y of mu be equal to the cotangent bundle of the flag variety in mu steps in Cn. And we're going to study this v of mu will be, so this will be my category, will be the derived category of coherent sheaves on this y mu. And now sometimes at this point in my talk, people ask me, why do you work with cotangent bundles? But since you were at the previous talk, you won't ask me this question, because you know that the reason why I work with cotangent bundles in some sense is because these actions come from V modules here, and then we get the coherent sheaves. That's one philosophical reason why it makes sense to work with coherent sheaves. Okay. So we'll define a categorical SLN action where these are the varieties. I mean, these are the categories. Sorry. And the functors. So VI. So now I define functors. By the following diagram, which is similar to Rouquier and Khovanov-Lauda. Before I do that, so one can describe the points of this cotangent bundle in a very explicit way, which will be kind of, not really important, but sort of cute. So we can define the points of this thing in the following way as pairs x v dot, where v dot is in the base, in the flag, in this partial flag variety. X is an endomorphism of the vector space, and x vi contains the dimension. So then we can define a correspondence diagram WI between the flag variety where the jumps are mu and the flag variety where the jumps are mu plus alpha I. Notice that the dimensions of the pieces of the flags here and here are the same, except the ith one gets one bigger. That makes the jump at the ith spot one bigger and the jump at the next spot one smaller. That's this alpha I. So this Wi will be triples, we can define a correspondence, will be triples x v prime, such that x v dot is in cotangent bundles of the flag variety. Use that flag variety in Cn. X v wieder frei. And Vj is equal to Vj prime, Vj not equal to I, and Vi is contained in Vi prime. So this variety is exactly this kind of conormal bundle variety that's happening over time. So this correspondence, the space which sits between these two varieties, will be used to define a functor EI. So I define it. So the space comes with two projections, and we call it phi 1 and phi 2. So I define EI from the derived category of coherent sheaves on the one side to the derived category of coherent sheaves on the other side. Well, what can you do with coherent sheaves? Well, you can take pull back. So here F, you can pull it back to here. So think of it as a vector bundle. This is like a pullback of vector bundles. Then actually there's some specific line bundle which I'm not really going to define exactly, so let's call it Li. We can tensor our, say, vector bundle by this line bundle, and then we can push it forward. So this push forward step's sort of hard to think about when you think about vector bundles. So it's like taking the cohomology of the vector bundle along the fibers and that type. Okay, but anyway, there is such a functor between the derived category coherent sheaves here and here. Call it EI, and FI, a similar kind of formula, except the line bundle is a little bit different. So those are my functors, EIs and FIs. So at this point, what I would like to say, so this is, remember, this is going to show us to be part of the data of my categorical G action, or in this case, categorical S-line action, right? So the data of categorical S-line action was a bunch of categories. These are my categories, a bunch of these functors, EIs and FIs, moving between them. And if I really want to get the two categories to act, I should now specify a bunch of natural transformations of functors. And this turns out to be kind of hard to do, and because it was hard to do, we kind of invented a different notion, which sort of you should think of as kind of sitting between the naive categorical action and the true categorical action. Well, maybe sitting much closer to the true side. Okay, so a geometric categorical G gamma action consists of the following data. So, one, sequence of smooth varieties. And these smooth varieties will become categories produced by considering the derived categories of coherent sheaves. So we definitely have that in our situation. Second piece of data, which is going to be functors. So functors from the derived categories EIs, from the derived categories of coherent sheaves on these varieties to the derived categories of coherent sheaves. Okay, so similar for FIs. So for the moment, this is looking like either the naive action or a true action. So if it was a true action, I would now specify some additional data of natural transformations coming from those diagrammatics that Rouquier told us about. But that becomes a bit complicated, so we had some kind of shortcut. So piece of third data is more geometric data. So it consists of some deformations. So some other varieties, y is mu tilde, which maps to C to the I, such that the central fiber is the original variety y of mu. So the kind of main technical thing I want to tell you in my talk is that we're able to replace all this business of the natural transformations by just this geometric information of the deformations. And intuitive reason for this is because if you have a one-parameter family of deformations, you can construct this certain morphism, which is a composition of the Kodaira-Spencer class of deformation with the Tia class, and this will essentially replace this guy with the dot. So this guy with the dot is somehow being replaced by these deformations, and then the rest of the data comes along as well. So there'll be some conditions plus. So this is the data, and then there'll be some axioms this has to satisfy. But I don't want to write them down, but they're not that bad. Like they're maybe I would say less involved than if you're having an action of the two category.
Maybe you can say what C to the I is?
Oh, C, I is the finite set, and C to the I is the finite set.
Sorry, which finite set?
I mean, I is the set of vertices of the Zinkin diagram of
Okay.
this graph, yeah. So you can think of this as the Cartan algebra H.
So these axioms do not imply the Khovanov-Lauda axioms.
Well, it's so.
Okay.
Geometric, categorical. You can actually on varieties. Y mu gives rise to an action of the two categories. Two categories of Khovanov-Lauda or of the two categories of Rouquier on the derived categories of the coherent sheaves of this right. So I should say this conjecture is actually proven in one example. So it's proven when G is equal to SL2, and where we use the Rouquier 2 category, or instead of the Khovanov-Lauda 2 category. And on the other hand, it's kind of maybe believed that under some technical assumptions that these kinds of Rouquier actions of this Rouquier 2 category is the same as actions of the Khovanov-Lauda 2 category. So this conjecture maybe not that far away from, say, being tried to prove in general.
Describe a bit more, how to translate a deformation of these varieties into functors.
Not functors, natural transformations between them.
Into natural transformations.
So there's it's going to be slightly technical. How much time is left in the talk? No, I can do it.
Talk about 25 minutes.
Whoa, really? I've been talking fast. Okay, then I can do it. Okay. So these, I didn't actually say it right here, but one condition I want on these functors is that they're of a kind of geometric origin. In other words, they come from a sheaf on the product. So I comes from a sheaf. The I on the product. So this is inside the derived category of coherent sheaves of y of u plus y of u plus alpha I. And so that's the first thing. And the second thing that I want to say is if we have the following situation, any variety with a deformation mapping to C, and we take the central fiber, then one can, and E is a sheaf on Y, then we can construct a morphism. Then we can consider the push forward. So let me denote this thing I. We can take the push forward of our sheaf, or complex of sheaves, and then pull it back. And there exists a distinguished triangle which relates this thing to the original sheaf we started with, and the original sheaf we started with shifted by 1 homological. Okay? And from this distinguished triangle, you get a connecting morphism for this distinguished triangle, which looks like this. And that, so if you use this thing is called this thing is essentially the obstruction to deforming E in the family. So you have a sheaf on the central fiber, it's obstruction to getting it to become a sheaf on the y tilde. This was studied by Quiver. Thomas.
Guys, this is when you said Kadira with
And TI. Oh yeah, you're the expert in this.
no curvature for me.
And I forgot though. And so this guy, the dot, which is as we know from parents' talks, a map like this. This dot guy is coming from using this sheaf EI here together with a certain one-parameter subfamily of the definition. And in fact, all of these axioms are phrased in terms of this sheaf deforming or not, these sheaves deforming or not deforming in this family, along certain one-dimensional pieces. So somehow, this kind of geometry about sheaf is deforming or not deforming in this family is all about, that's what these axioms here are about. So something very easy to check. Let me give you an example of this family, I guess. So, or I can say the theorem, I guess. So the theorem is that there is geometric categorical G-action on this unions from the collection of all cotangent bundles of these five values ECN. So I've told you most of the data. I've already told you the functors and I told you the varieties. So the only last piece of the data is to tell you what the deformations are, which is, as I'm emphasizing, is analogous to telling you what the natural transformations of functors are, but much more geometric. So it consists of, so if this was, space here was pairs x and v with this property. This is triples x v dot little x, which is the x, little x1 and little x minus 1, such that x of vi is contained in vi, and like before where it was sort of sent down, but x acting on each quotient vi mod vi minus 1, x by a scalar xy, x times the identity. So this thing clearly maps to the space C to the n minus 1, where you remember these numbers, and this is a deformation. So the simplest example of this, say from a geometric point of view, is you can take a cotangent bundle of P1, and you can deform it. Symplectic geometers are familiar with. This is like the deformation of the A1 singular. Okay, so as I mentioned, so let's just recap what I've been saying so far. So I started the talk by saying we were interested in braid group actions. I said for braid group actions, actually, we're going to look at categorical Lie algebra quantum group actions. And then I stated this theorem that said if we had the categorical Lie algebra action, true categorical Lie algebra action, then we got a braid group action. Now I said, well, it's hard to get in these geometric situations true actions of these two categories, so we invented this new notion, geometric categorical G-gamma action, and we only have a conjecture that it gives you the same actions. But the sort of saving point is the following. That the theorem that I stated earlier is true for these geometric categorical actions as well. It is also. So this paper, I think, appeared earlier this year. So given in December, geometric, either in December or January, given a geometric categorical G-gamma action, so that's the notion there, on sigma I from d of y of mu's to d of y of mu's plus alpha I, satisfying braid relations. So the way the logic works out for this is that to construct the sigma I, so the kind of logic. So to construct the sigma I, we use that geometric SL2 implies, so we use the proven part of that conjecture. It implies Rouquier SL2. And then we use that Rouquier SL2 implies that complex that I wrote down earlier with those EI, Ks, and so on is an equivalence. So this step was proven in the previous work with Sap and Tony, and this step was also proven in a previous work with Sap and Tony using previous work of Rouquier and Khovanov-Lauda. So that's to construct the generators of the braid group, and for the relations, well, this part is sort of not easy to summarize in 2 words, but it really uses the axioms directly of some aspects of this deformations directly. So, but sort of in a very minimal kind of way. Use the geometry. Okay.
What category does sigma I take you to?
Sorry?
What's the image of the thing on the right-hand side of it? I mean, that's not SI.
Yeah, oh, whoops. Yeah, it should have been. Thank you. Thank you. So just to discuss an example in a little more detail here. So let's imagine that little n is equal to big N. Okay, so then we're studying. Then in this kind of example here, the mu is going to vary. So here mu is varying over all. The little n was fixed, the capital N was fixed, the mu is varying over all. Ways to write capital N as a sum of ordered sum of little n things. So in this case, you can write it as 1, 1, 1, 1, 1, and that corresponds to the full flag variety. So in this case, it's the kind of zero weight space of the representation, or the categorical representation, is tangent 1, 1, 1, 1, 1, cotangent of flags 1, 1, 1, 1, 1, Cn, and this is also known as the full flag variety of Cn. Right, but it's the representation. But I mean, this is the ordinary full flag variety in Cn. And so these theorems, give of the braid group on the derived category of coherent sheaves on this full flag variety of the rotating bundle of Cn. And this action was previously constructed. Already constructed. Because by 2 different groups. One is delano hypothesis. And the second group was Rouquier-Khovanov-Lauda. Now I should note that in this case is somehow, in some sense, the simplest case, it turns out, of our thing, because in these cases, this whole long complex just reduces to 2 terms. The generators of the braid group act by what's called spherical twists, so some kind of particular special kind of 2-term complex. So So one way to think about this kinds of actions, so actions of the braid group on these categories, is as the generalizations of, so instead of just spherical twists, we have these kind of longer complexes, and anyway, so we have these longer complexes obeying the braid relation, generalizing this. Yeah. And now so all this was just for SLN, so certain categories for SLN. Now, I just want to switch gears slightly. We can talk a little bit about quiver varieties. Quiver varieties. So we again fix an arbitrary gap now. And then given two sequences of natural numbers, v1 up to vn, we call it vi, I and I, wi, I and I, we call it special sequences v and w, Nakajima constructed some quiver variety. So it's related, it's a kind of variety of certain kinds of representations of a quiver associated to gamma. I won't go into the exact detail, but it generalizes the cotangent bundle of partial flag varieties. So these are all examples of these things. And let's fix the W sequence and allow mu to vary. So then we can take the direct sum over all V's. Sorry, fix the W's and allow the V's to vary. And let's consider the cohomology of these varieties. And W. So Nakajima constructed an action by correspondences. In other words, the generators of the Lie algebra acted by correspondences, an action of G gamma by correspondences on this cohomology. So it became natural to try to lift this action on the cohomology by these correspondences, to use this kind of, in some sense, the same correspondences and try to make it work in the derived category, the categorical action. And this, it sounds kind of simple, but it somehow turned out to be relatively complicated. So this, not really very complicated, but all sorts of little technical issues along the way. So this will be a paper which will hopefully appear later this summer. So for the following, so there is categorical G gamma action on the collection of these varieties. These four varieties. From here, W is fixed in V varies. And so in particular, this kind of construction allows you to give, say, categorification using this geometry of all your useful representations of these kinds of ideologies. And also, you can then apply this machinery of braid group actions coming from geometric categorical G gamma actions to get a bunch of braid group actions here too. But I don't really know of any of them that are particularly kind of more interesting than the ones from the cotangent bundle of flag varieties. So it goes from EI, EJ, EJ, yeah. So make sure we get this right. So in some sense, okay. So when I is equal to j, the way this guy is defined is sort of in a slightly, well, we just proved that there's a one-dimensional space of such things under our assumptions, and you just choose one of them. And I guess when I is not equal to j, that's also what we do. So yeah, so that's kind of the answer. So it's not defined in some kind of canonical fashion, just by making a choice.
I'm sorry, so we were looking for morphism, say, between EI and EI. So EI is a sheaf on the cross product. So you were not looking for all the heads. You wanted some particular ones that say work in your construction or
Yeah. I mean, the advantage of producing X by this, the advantage of producing morphism by this recipe is that you can kind of relate the properties of this morphism to this deformation, and hence be able to prove things about this morphism.
you need to use this one. All others you just disregard.
You mean other maps between E and E shifted by 2? Yeah. Yeah, that's almost true. It turns out at the end we have, there's some kind of strange thing where you have to go back and tweak the thing. So it might actually, in some sense this is like we kind of want this dot to map to, but it's possible that we end up having to tweak it by some other things. There's some like technicalities, but basically yes, we take this guy.
So in your construction of Khovanov-Lauda for this method, is there any way that do you have any natural algebraic sort of extra terms that you could throw to get a special sequence of Khovanov-Lauda or something else? I'm just thinking about, there's, in level closed format covariance, there's algebraic interpretation, Donaldson invariance. If you could somehow see Rook as a special sequence from an algebraic perspective.
Well, we never thought about it, but maybe, I don't know. I don't know. Possible. Also the tensor products of previous representations. By looking at certain, so Nakajima defined these certain sub-varieties of these quiver varieties called tensor product varieties, and when you look at the sheaves supported on those sub-varieties, it categorifies it's slightly more complicated than that, but roughly that's it. There's some strange caveat, which is that actually when for some kind of technical reasons, it only seems you can categorify the Q equals 1 representations, not the arbitrary Q representations. Even though on these spaces, on this space actually there's an action, well I wrote here UG, but there's actually an action of UQG gamma, but it's sort of somehow hard to pick out the ERF if you're thinking about it as a UQG rep, but it's easier to pick out the ERF if you think about it as a G gamma rep. Other questions?
Thanks.
So, the key one is how you actually feed it. Great. In the sense